Final talk in the session is visible and near-infrared reflectance of mineral mixtures and nanophase iron under anoxic conditions. Talk will be given by Chip Legett.
All right, good afternoon. I'm going to be telling you a little bit about some of the first results from a series of experiments that we did at Temple University last September. So all of these experiments are designed to kind of replicate the mineralogical systems that we often see in space weathered materials relevant to the moon, but they're not meant to be perfect analogs. I'll get more into that here in a second. So first off, what is space weathering? The often cited Peters Noble 2016 calls it the gradual alteration of materials when they are exposed to a variety of natural processes that occur in the space environment. Basically, if you put it in space and it changes, it's probably due to space weathering. For our purposes, these processes vary by location, and we're looking mainly at 1AU, where the moon is, and are looking pretty much only at micrometeorite bombardment and the effects that it has, as well as the effects directly due to the solar wind. Looking at what this looks like in remote sensing data, if you, let's see if I can get this thing to work. Maybe, there we go. If you look at a soil, you get this kind of flat, steep red profile compared to the similar composition bulk rock that's nearby. You have the nice diagnostic absorption features. So you tend to get darker spectrum, redder spectrum, and a loss of spectral contrast as the result of space weathering. And this can make it difficult to determine the composition of these surfaces remotely. These are some TEM images of a space weathered rim on, I believe this one was a feldspar grain. And you can see over here in the TEM bright field image these little black dots around the rim of this particle here, and those are nanophase iron particles. These rims are amorphous and compositionally distinct from the grains that they form on. And while these things can be mixed phased, a lot of times we see them as single domain iron. So Kate Burgess and Rhonda Stroud have some results showing that there may be some oxidized iron in these in a recent paper. And it really shouldn't surprise us that it's hard to figure out what these things look like in remote sensing data, because they are geometrically and compositionally similar to materials used on stealth aircraft called iron ball paint. I asked a friend that's an engineer on the if I could have a sample of skin to play with to try to figure this out. He didn't seem to think that was a reasonable request. So looking at a model of one of these grains, kind of what we're doing in this experimental work is we use 30 nanometer diameter iron particles that we purchased as such, and that were shipped and kept under anoxic conditions. And we mixed them with sub-10 micron olivine, feldspar, and pyroxene. So if this is kind of a conceptual model of what a space weathered grain might look like, where you have a central host grain, the pointer's not going to work. Central host grain of some diameter with a thin rim on top of it, and then embedded in that rim are those nanophase iron particles. We are kind of approximating this by just getting rid of the rim and mixing the nanoparticles in with these small grains to see what that looks like. So our compositional system that we worked with here, we had 2 component mixtures of olivine, augite, and labradorite mixed with various amounts of iron, and then 3 component mixtures where labradorite made up the bulk of the sample with a little bit of either olivine or pyroxene, and then some amount of iron with it. I won't read the chart of weight percents and everything here, but it was very consistent. We did this all at Temple University in Steve Kimtaub's anaerobic chamber, so that the iron nanoparticles were never exposed to air and water. So the idea here is if you expose a 30 nanometer iron particle to the Earth's atmosphere, you no longer have a 30 nanometer iron particle, you have a 30 nanometer iron oxide particle. And so to avoid that, we just did everything in an argon environment. We ran the fiber from our Field Spec 3 spectrometer through a port into the chamber, put the light source in the chamber, and collected all of the measurements internally, referenced to Spectralon. And anything that I show that was generated with software, you can get a copy of that script or Jupyter Notebook or whatever it is on GitHub. And I warn you, I do not guarantee that any of this will work predictably, but you can see what I used to generate it. So this is what our entire messy data set looks like. And don't worry about this slide. I'm just showing you how many samples we had and roughly what it looks like. So it's color-coded by sample family, and let's look at one of those now, which is the two-component family of olivine with iron. So the blue line at the top here is the pure olivine spectrum that has no iron mixed with it. Then we have half weight percent iron, 1, 2, and 5 weight percent iron mixed in with it. And so the first thing to notice is that we see all three of the kind of characteristic effects of space weathering optically in these samples. We see them generally darken, redden, and we see a loss of those diagnostic absorption features, especially the 1 micron feature in the olivine. Interestingly, this one actually, my turn to mess that up. We see over here on the longer wavelength side that this sample appears to have gotten brighter at the longer wavelengths. And I'm not 100% sure that that's real, but I'd say that it's better than 90% chance that that actually came out that way. So, and that would be an example of a case where the reddening effect was greater than the darkening effect. Looking at band depth, we decided to first try the modified Gaussian model to quantify the effects of that spectral contrast loss. So this is that pure olivine sample, and we've fit 3 Gaussians to it, and we get a really good fit on this sample. But as anyone that's worked with MGM knows, it doesn't handle low contrast samples all that well. And in fact, when you start looking at increasing amounts of olivine, this one down here on the bottom left is only 2% iron. That one's 2% iron, and we've lost one of the Gaussians. It's setting the intensity basically to 0, and they keep getting wider and wider and shifting to longer wavelengths. So while you can fit this, you basically have to know what the answer is before you fit it, or at least what a reasonable answer is before you try fitting it. Otherwise, it's just going to optimize the curve fit, and it may not actually apply to an absorption. So this one over here is another example. This is one of the 3-component mixtures with, that's mainly feldspar. And trying to fit that, we couldn't really get a comfortable result with it. So what we did is centered everything. So I just subtracted the mean value of each spectrum from the value of that spectrum so that it has an average reflectance of 0. An average reflectance amount. It's no longer in reflectance space. And then decided to try to quantify things this way. So first, I can quantify the darkening by just saying what's the change in average albedo. I can fit a linear solution to this and get a slope out of that, and that's what we'll use for slope. And then this band depth parameter, I'm just going to take the max value and the min value in the range of interest and say, okay, that is what we're using as a proxy for contrast, or band depth using the term loosely. Looking at what we get out of that with one of the 2-component mixtures and one of the 3-component mixtures, we see fairly consistent results. You get this very kind of typical darkening regime in the upper left here, where it looks a lot like an increase in the absorption constant. It's a logarithmic decrease in reflectance. The slope shows a more interesting trend, where we see it go from actually blue in both of these samples, meaning the linear fit was tilted down towards longer wavelengths, to a big jump to a red slope, and then it kind of starts decreasing as you add more iron and it gets darker and flatter just because you're approaching the spectrum of iron. My contrast parameter looks an awful lot like albedo, kind of just conceptually, where you see this same kind of maybe logarithmic decrease in total contrast. So plotting those 3 up together on a ternary diagram, where we have redder slopes at the top, brighter spectra at the bottom left, and more contrast at the bottom right, we can start to see how these things change as you add iron to the entire data set. And the first thing to notice is that the blue line here is kind of indicative of all the 3-component mixtures. The red circles are the only one that's a 2-component mixture here. And so you see they all start over in that bottom left-hand corner and move up and to the right. The two-component mixture, on the other hand, seems to follow a different path, meaning that we might not expect the changes as a function of weight percent iron to be the same in a two-component versus three-component system or with different host mineralogies. And so we're going to have to be careful about tracking that. So what we decided to try was principal component analysis on this data set. If you're not familiar with principal component analysis, it transforms your data set into a series of orthogonal measures that maximize variance. So the first principal component accounts for the most variance in the sample, the second most, and so forth. And in spectral data, you can have basically each one of your wavelengths can be thought of as a different dimension to your data, so you can have as many principal components as you have wavelengths. Thankfully, you don't need that many because that would be a little over 2,000 for our data. The new basis of this, once you do a principal component, is not necessarily physical. It is just a math algorithm that maximizes a function. So you have to be careful when you're drawing comparisons to a physical parameter with this, but you can relate it. This is what the first two principal components of the solution for the olivine and iron two-component mixtures looks like. And if you're familiar with the spectra of olivine, that principal component 2, the orange line, looks a whole lot like an upside-down olivine spectrum. So this is one of those cases where that is not olivine because it's a principal component, but it's probably very closely related to it. When you do principal component analysis, one of the questions you have to answer is how many principal components do I need to adequately model this data set? And so one of the things you can do is plot a scree plot here that shows the total variance or cumulative variance accounted for in a number of components. So down here in the bottom left, the first component accounts for roughly 72.5% of the variance. The second component, we're up to 99.8, and then we basically don't get anything better. So in this data set, you only really need two principal components to adequately reproduce the features of the system. Plotting those two components against weight percent iron, we see a nice trend, especially in principal component 2, that correlates really well with the change in mineralogy. So if these R-squared values are for linear fits to the data, if you do a log fit on those 4 data points, you get an R-squared of better than 0.95. So now we're really being able to relate this back to something. In the 3-component systems, here I let it use 3 principal components just to kind of mimic the number of minerals that we have. We're starting to see things that are less obviously related to the mineralogy, but still there. So you can see out here there's kind of a 1.9 micron feature that's inverted that's probably related to water. We only really need 2 principal components to account for 99.9% of this data set, but leaving the third one in is just basically noise. It's not going to hurt anything. And plotting those up again, the second principal component, which was the orange line here, again, seems well correlated with composition. So we don't have kind of an overarching conclusion for this yet, but it suggests that the principal component analysis may be a tool that we can use to further analyze this data set. So in conclusion, our samples do show all 3 of these kind of hallmarks of space weathering in our mixtures. The 2 and 3 component mixtures both darken, redden, and lose contrast, but they might follow a slightly different path through that space. And these samples are probably too low contrast for techniques like MGM requiring the use of some alternative, which PCA might be a good one. We're going to try Dan Moriarty's PLC model on these next and see if we can get something out of that instead of MGM. And then I'd like to try a machine learning based model to see if we can train a neural network to reproduce these. And eventually I'll be dumping this into MSTM like the work that I've been doing for the past 4 years and seeing if we can duplicate it using that method. Real quick, some acknowledgements. This is the old version because Deanne is an author, not being acknowledged. But Ryan Collier at Cabrini University and then this list of chat channels on the IRC Freenode network have been really, really helpful with software, and I encourage you to try IRC if you ever need help figuring out how to write something.
Some time for questions.
Iron doesn't like to stick very well to oxides, so it'll diffuse around. So do you have evidence that these particles stay particles, or that you don't have an agglomeration in a large
No.
iron particle which has massive optical absorption?
No, we have not examined these in an electron microscope or anything. When we put them into the anaerobic chamber, they were in the sealed container, like triple bagged sealed container that came from the manufacturer. We opened it, we used an agate mortar and pestle to kind of gently grind it to mix it until it was visually homogeneous, and then measured the reflectance of that sample. But we have not done anything that approaches a nanoscale examination of these things.
In fact, weren't the iron particles electrostatically just like, flying off all over the place?
Yeah, okay, so then they have a surfactant on them or something that protects them from finding each
We
other?
specifically bought the
Yeah.
ones that did not come coated.
So how will they charge then if they're fully metallic?
They're supposed to be uncoated from the manufacturer. That's what the bag said.
Let me just say something. If a chemist says it's clean, maybe it's not.
Yeah, like wards, yeah. I'm a little nervous about the PCA because, as you mentioned, you can't really
Yeah.
put your finger on what it's doing. But I have a general question, and you went by it quickly that I didn't quite get it. When you said some people call it normalized or scaled, when you got, you said you subtracted a value to get, and that's, did you really mean subtraction?
Yes. So there are two things that you can do to the data set depending on which method you're using. The first one is centering the data set, and the second one is scaling the data.
Yeah.
So we did not scale this data because it is all reflectance with the same set of units, so it does not need to be standardized to the one standard deviation like some other data sets might. All we did was remove the mean value of the data set from it.
That affects, well, okay, then the slope that you get then is very dependent on the albedo.
That's why we got rid of albedo.
Well,
Oh, I see what you're saying. I see what you're saying.
So
Let me-
we're not talking the same
Yeah.
language then
I gotcha.
for what we do normally with remote.
We did a test for this, and I left it alone and reran it and got exactly the same results to 3 or 4 decimal places if I didn't center the data or if I did.
I mean, if you scaled it rather
No,
than,
I'm saying like I took the raw data just
Yeah.
in reflectance space without massaging it at all.
Right.
No pre-processing.
right?
I filtered it, but other than that, no pre-processing. And I took this data set, which is the same thing except for mean subtracted from the spectrum, and got the same results.
When you say slope.
I'm sorry.
Yeah, well, there's a lot of different definitions of slope in the community too. So which slope are you measuring when you measure the slope here?
I fit a linear regression to the entire spectrum over the wavelength range that's displayed,
Yeah.
and take the slope of the linear fit as the average slope of that spectrum,
Delta X over delta Y.
basically. Well,
Because-
yeah.
Because mathematically, I'm not sure what you're doing is the same as what we normally do with the remote data, where we actually scale things. So
Okay.
that removes the albedo, but it maintains the color.
Okay.
And if you do subtraction, the color, you get color variations, but you're not measuring the same thing.
The delta reflectance should be the same, the way that I'm doing it. So maybe I'm describing it poorly, but from the
Yeah,
minimum point to
we
the
can
maximum
talk.
point is the same before and after I center it. If that's what you're, so like, if you have a 10% reflectance, or 0.1 reflectance change from lowest point to
Yeah.
highest point, that's preserved.
Well, yeah, but that's a subtraction. Why we often talk about scaling is that kind of color, if we were to say a color ratio in a multispectral imaging, we know that essentially is doing scaling. You know, when we
Okay.
say this is 10% bluer or redder, it's because it's a ratio. And so scale data needs to have, scaled so that we can get that kind of color ratio.
Okay.
When you do a difference, mathematically it's different, and you won't get the same
Right.
answer.
I have that data. I also have a center and scaled data set prepared for this.
Okay.
I didn't include it because I didn't think it was necessary, but I would love to talk to you about this, because if it's available, all I have to do is rerun a worksheet and I've got the new figures.
Okay, well, I would, yeah, I'd recommend working with the scaled if you can, simply because when we have hyperspectral data, et cetera, and we look for color variations, that's what we do. We do a color ratio to see what the variations as a function of spatial relations are, which is a scaling effect, essentially. So if you want to keep on that same venue, then you'd probably be better off scaling rather than doing the difference.
Okay.
That's
Dan?
Yeah, just kind of to follow up on that.
Just wait for the microphone so anybody online can listen.
Yeah, so Carly, just to follow up on that, Chip mentioned some future work using the PLC method, and you'll get those scaled slopes right out of that, so that, that'll be a good confirmation of that.
Should go without saying, but we've just moved right into the discussion section.
Just to comment on your principal components, they seem to track pretty well with the way principal components fall out for things like asteroid taxonomy. So basically, the first is going to be sloped, and the second is going to be bands and band contrast. And then everything after that is noise.
Yeah. That's entirely consistent with the 65 spectra that we collected.
All right, let me just check the schedule here. So we are, we are available to have additional discussion for about 2 minutes. So any other questions? Is Alberto still online, or did he take off? So I'm happy to entertain any additional questions. If there's any other questions for Chip, you can take them now. Otherwise, you can have 2 extra minutes to go to the bathroom before we go to the plenary. Did I hear something?
I am available. I don't know if you can hear me.
And Alberto's here too.
I am available.
Thank you.
So we've been playing with the
Yeah.
principal component analysis for extremely complex mass spec. And we found that a machine learning algorithm is better. So
Yeah.
is that the path you're going, or?
The trade-off is that the machine learning algorithms seem to work better, but you need a lot more data to make them work. So if you're talking about something like a neural network, you need 3 independent data sets that don't overlap in order to train and evaluate that neural network. And when you're talking about like our work, we have 65 samples. So the probability of us successfully training a neural net on doing training, optimizing, and validating on 65 samples,
Not
it's
enough.
yeah. If you got 10,000, it's great.
Well, you can spend another 5 years. And
I did want to throw my hat in on the swirls comment from earlier. This could just be a kinetic issue, right? If the hydrogen or the protons that are being implanted are going to gradually change the redox state of the rims over time, it might just be that on the moon they've been sitting there long enough with this hydrogen present that we see these changes, whereas in the laboratory when we're bombarding this with protons and we spend 8 hours doing it at room temperature, that we're just not overcoming that kind of kinetic barrier. And that the micrometeorite impacts of the lasers or whatever it is that we're simulating it with is providing the activation energy necessary to cause that change. So instead of thinking of this as like a process-dependent effect, it could be something as simple as we don't have 3 billion years to sit around and see what happens.
Thermal cycling.
Yeah.
all right, let's thank Chip and Alberto and me again.